These are the linear motion problems. They were due on October 9th. I know a lot of people had trouble with these, but I also think a lot of people probably didn't put in the time they needed to look at my notes, um, get some practice, go on the physics classroom, things like that. So these are the answers. I'm going to go through a little bit of how to get those. So you can look at the PDF or look through here when we're talking about them. And I'll definitely go over number 8 in class at some point. All right, let's go back to the top. So with PC-24, it's a boat that's accelerating from rest. So there really are a few formulas to use. This is the version of the one with position, acceleration, and time. And this is on your formula sheet, but it looks a little different as we talked about. Notice I don't need the more complicated version of that formula because there is no initial velocity. It starts from rest. So to find the distance traveled, that would equal to the displacement in this case. Simply 1/2 acceleration times squared, and that's about 49 meters. For PC number 2, in this case this is a funny car competition, so it gives you the time it takes to go a 1/4 mile, and it's asking about the acceleration and the final velocity. So the first thing I need to do is, actually part A is asking about the average velocity. So I know the time. I've got to convert miles to meters. So 1/4 miles, or 1/4 of a mile, pardon me, times 1,609 meters per mile is equal to 402 meters. Actually, I think it's 402.25, but I rounded off. So the average velocity is just that change in position over the time interval. It's 90.6 meters per second. For letter B, it's asking about the average acceleration. So you could do this a few ways. For example, change in velocity over change in time. And this is another way. The problem with the change in velocity over change in time is you can't plug in 90.6 for the change in velocity because that's an average velocity, not a change. If you start at 0, and this is your average, your final velocity is not 90.6. So I X'd that out, and I'm not using it. In fact, I can show that in a little bit, that I will X that out. Big X there. Let's make it big, change the color. I like it. Nope, we're not going to do that. Okay, so I need to use the same formula I did before. Change in position, acceleration, and time. I have to rearrange that to get acceleration. So you need to be algebraically able to do that. Whether that is through your past understanding of algebra or ALEKS or asking me or practice does not matter. So that you come up with an acceleration of around 41 meters per second squared. Now we can find the final velocity pretty easily. You could use either of these mathematical formulas to do that. They give the same answer. I use the top one. Final velocity is equal to 0 because it wasn't moving at the beginning. The acceleration times time. So for every 1 second, we're increasing our velocity by 40.9 meters per second. So that's an acceleration of 40.9 meters per second times the time gives us our final velocity. Notice it's about twice what the average was. That should make sense. For number 13, I redrew the graph for this. So part A was asking about the acceleration of the car. I could get this either by this mathematical model. I know the final and initial velocities and the time. Or I could recognize that's the slope of the graph. So if I go from 18 to 0 in 6 seconds, the slope of that graph is negative 3 meters per second squared. To find the distance traveled, I could either get the area of the graph, which is 1/2 height times base, or I could have used this formula, recognizing that this is a positive velocity and this would be a negative acceleration. If I use those both correctly and with the correct signs, it would give me 54 meters. For 18 did not have a graph shown, but I made a graph. I knew that this plane had to end up at 28 meters per second. It started at 0 and an acceleration of 1.9 meters per second squared. So that tells me I need to end up here. I've got a slope of 1.9 meters per second squared. So I could have simply taken this velocity divided by this acceleration, and that would let me know how much time it takes to get to that velocity. That's what I've got in blue here. If I wanted to then use that, I could get the area 1/2 times this height times this time, and I think I did this in one of my classes. It was somewhere around 14 seconds, maybe, something like that, 15. And I could get this same change in position. Or I could use this mathematical model, which does not have time in the equation, and figure it out that way, and that's what I did. Again, notice I'm solving for something that's not just all by itself on the left side. That means I've got to do a little bit of algebra. PC20 was talking about Susie loves to ski, going down a slope, so she starts at this speed, she ends at this speed, in that amount of time. That's a negative acceleration, so that should be pretty straightforward formula. Negative 18.8 meters per second squared. To find the distance she traveled, again, I would use this. You could have used a different formula, such as this, because you know all that information, except the delta x. So that's how I get 22.3 meters. Oh, I set that down there in red. For PC28, very similar. The key thing here, I think, is recognizing that this is an initial velocity. Notice I almost boogered that up. I kind of wrote over that, because that's the velocity the camera starts to fall. The change in position is 52 meters, and it's accelerating as long as it's in the air until it hits the ground. So I use this formula again to find my final velocity. Ends up being 33.6 meters per second. If I know my initial velocity and my final velocity and my acceleration, I can find the time it takes to fall. And for number 30, this is, again, recognizing that this is really vertically, so we would probably should call that delta y instead of delta x. It doesn't particularly matter as long as you understand what you're doing. Find the time to fall, if you know the change in position, which is 132 meters, and acceleration. It's about 5.2 seconds. And then we can use that to find the final speed. So I think the key thing is seeing these patterns over and over, and that's going to help you understand how to mathematically attack things. Number 8 is a little bit different. It's something that's projected straight up and comes straight down. And so I drew a picture because that helps me visualize it. All we were told is this is 3.56 seconds total time in the air. And we were asked to figure out the speed at which it's thrown and how high it rose, which is the maximum height. So the key is looking at free information. And I'll probably go over this one in class. But for example, if the total time is 3.56 seconds and it goes up and comes down to the same height, it should make sense that there's some symmetry here. So the time to the tippy top is about 1.78 seconds. Also, the time up would equal the time down. And again, each of those is half the total time. So therefore, you should think that the initial speed with which it's thrown would also equal the speed right before it hits the ground or hits that location again. Now, the speed's the same, the velocity is in different directions. So for me, it helps to think about this, to think about half of the trip, either the part up or the part down. I actually normally like to think about the downward part, the second half of the trip, because gravity's pointing down, so I can think of that as positive. The motion's down, I can think of that as positive, and I don't have to worry about screwing up how to use a negative sign. So thinking about this, oh, and I know the other free information is that the speed at the tippy top is 0 meters per second. We saw that in our ball toss lab. So I can think about the trip down, and I know that the initial velocity from the tippy top is 0 meters per second. We know what gravity's acceleration is, and we know that the time down is going to be half of the total, that's 1.78 seconds. So the final speed is going to be 17.4 meters per second, therefore the thrown speed would be 17.4 meters per second. Again, this is ignoring air resistance, which in real life has significant effects above decent distances. This is thinking about the second part of the problem, and it's asking about the maximum height. So I could think about the first part of the trip or the second part of the trip with this. but the ball reaches its maximum height at t1 half at 1.78 seconds. It does not reach its maximum height after 3.56 seconds because it's actually falling back down to the same height where you threw it. So with that being said, I can think of the first half of the trip, in which case I would have this VI as negative and the acceleration be positive, or I can think the second half of the trip where this is 0 and downward is positive. Either way, it's going to get me the same magnitude of answer. So I like the 0 here because it makes my life easier. And so I have 0 times t plus 1 half a t1 half squared because it's only falling from the maximum height for 1.78 seconds. So that'll let me know its maximum height from the point where it's at its peak when it's coming down for 1.78 seconds, and that's about 15.5 meters. If you use the whole time up here, notice this would get you 4 times the distance, so that's about 62 meters. So hopefully that's helpful, and if you have questions, please ask during E&I or after school.